climate change. Þannig að þá sjáumst bæði við og þetta. Flott, þetta fínt.
Let us give one more minute before we start. People are joining. Welcome. Good morning, good evening, depending on where you are located. I am Soumitra Das, President of the Healthy Climate Initiative and a Wharton graduate. It is my pleasure to join you today. Over the last 2 days, we discussed climate adaptation and mitigation. Today's topic is climate restoration, a very important topic to make climate safe and healthy. Why is climate restoration important? The reason is that the mitigation efforts to reduce carbon dioxide emissions will slow down global warming, but will not stop it, because more carbon dioxide will be added to the atmosphere, and most of the global cryosphere will be melted by the time we achieve net zero carbon emissions. Given the current trend of carbon emissions, it is also doubtful that we would even reach net zero carbon emissions by 2050. Even if we achieve the Paris Climate Accord, global warming of 2 degrees Celsius would have devastating effects. Thus, the efforts to sequester carbon dioxide from the atmosphere and bring it back to the pre-industrial level and save the Arctic and third pole are critical to make the climate safe and healthy for future generations. We have 2 exciting panels to discuss these issues. Before I introduce our keynote speaker, I'd like to mention one housekeeping item. Please use the Q&A box to send your questions, not the chat box. Now we welcome our keynote speaker, His Excellency Olafur Ragnar Grimsson. Grimsson was the president of Iceland for 20 years, 1996 to 2016. He now serves as the chairman of the Arctic Circle, which he founded in 2013. For decades, Grimsson has been an active participant in the global climate dialogue, and during his presidency, he initiated and promoted clean energy proposals in Asia, Africa, the Middle East, Europe, the United States, and the Americas, especially using Icelandic achievements and technologies as a model. He's also involved in international cooperation on the oceans and the evolution of sustainable use of marine resources. Please join me in welcoming His Excellency Olafur Ragnar Grimsson. To you, Grimsson. Thank you.
Well, thank you very much for inviting me to participate in your dialogue and to address the crucial question of how we can take CO2 from the atmosphere and make sure it never again threatens the global climate. And I think it is appropriate that we have this discussion a few days after we concluded here in Iceland the large Arctic Circle Assembly, where over 1,500 participants from more than 50 countries came together to discuss the connection between the ice in the Arctic, the Earth's climate, and the need for a clean energy transformation. It was, in fact, the biggest multi-sectoral gathering in Europe since COVID started. And the last such big international European conference before the COP meeting starts in Glasgow. So I come to your dialogue with fresh impressions of how urgent this challenge has become. You might know that Iceland has the largest glaciers in Europe, and they are melting very fast indeed. They are also among the most studied glaciers in the world. Our next door neighbor is Greenland, the second largest ice sheet in the world apart from Antarctica. And Greenland had many representatives at the Arctic Circle Assembly. And the ice in Greenland is indeed also melting very fast. And as was pointed out at the assembly, if only a quarter of the Greenland ice sheet melts, that will lead to a global rise in sea level of 2 meters all over the world, in Asia, Africa, the Americas, anywhere, threatening thousands of coastal cities on every continent of our planet. And further north, we have the Arctic Ocean, and the aggressive melting of the Arctic sea ice is the major cause of extreme weather patterns all over the world, whether it is the winter snow in Texas or the changes in the monsoons in India. So, although it might sound paradoxical to people in faraway places, the melting of the ice in my global neighborhood is really the warning bell of what is happening. The only other inhabited part of the planet where you can witness this dramatic warning is, of course, the Himalayas, the so-called third pole area, where the glaciers that link China, India, Nepal, Bhutan, and others are also a reminder to all of us that the big rivers of Asia are being threatened, and over 1 billion people can suffer dramatic consequences if they continue to melt. And the reason why I mention this is that sometimes I feel like the discussion on climate change get lost in complicated concepts and almost scientific vocabulary. Whereas the melting of the ice, whether it is in the Arctic, in Greenland, in the Himalaya, the third pole, or in Antarctica, or in my own country, speaks for itself. And as I sometimes say to my American friends, the ice is neither a Democrat or a Republican. It's simply melting, warning us all of what is happening. And of course, we are all familiar about the agreement in Paris in 2015 and the urgency of the COP meeting coming up in Glasgow. Quite frankly, it is highly doubtful that the plans that have been announced by various governments will enable us to reduce the increase of CO2 in the atmosphere to a sufficient extent. So that is why I have increasingly argued that our immediate, as well as perhaps the most important task, is not just to reduce what we put into the atmosphere in the coming years and decades, but above all, to remove from the atmosphere the CO2 which is already there and store it in a way that it will never again threaten our planet. To be quite honest, I doubt highly whether we will succeed in the 1.5 degree target, even not succeed in the 2.5 target, unless we aggressively in the next 10 to 30 years take enormous amounts of CO2 from the atmosphere and make sure it is stored in a way it never threatens us again. I sometimes point out to people to illustrate this challenge that the age of petroleum and oil from the time of Henry Ford to this century was made possible by petroleum pumping stations all over the world, starting in the United States and going to Europe, but then to Asia and on every continent. And we're all familiar with the petroleum station, whether it's BP or Exxon or Shell or whatever, Sinopec in China, that allow us to drive up in our car and get the petroleum and oil and then go on. We now need to create a series of reverse pumping stations that take CO2 from the atmosphere, remove it for eternity, and pump it down into the ground. And the good news is the technology has arrived in the last 5 to 10, 15 years, that it is now technologically possible. And here in Iceland, we have one of the most remarkable examples of this possibility. Of course, there are a number of other projects in different parts of the world that have come forward in the recent even months or last few years, aimed at taking CO2 and pumping it down into the ground. But the Icelandic carb fix project is unique. It was started 15 years ago through a cooperation between Icelandic scientists, the Columbia University in the United States, and the Toulouse University in France. And for the following 5 to 7 years, a series of international scientific conferences and project and research was carried on, and the end result where I am sitting up at the Hellisheiði power plant. We now have the Carbfix station, which takes CO2 from the atmosphere, pumps it down through boreholes into the ground, where it touches base with basalt, and within 2 years turns into solid stone. Quite remarkable. I can tell you, when I first heard about this possibility, when the scientists came to my residence in the first decade of the century, it sounded to me like a science fiction. And I said to them, if this is possible, it will be revolutionary. And now they have proved it is possible. What is even more, it is commercially viable. So the Carbfix company has now announced plans to establish a terminal next to an aluminum smelter where there is a fantastic harbor, and bring the CO2 from Europe with vessels and then take it there and pump it into the ground. Next to the Carbfix station at the Hellisheiði power plant is also another remarkable innovation, which was created in Switzerland and then brought to Iceland, called Climeworks. That is an innovation that takes the CO2 from the atmosphere, gives it to Carbfix, which then pumps it down into the ground. It is an enterprise in which Bill Gates and a number of other famous international investors have now been partners of for a considerable time. For example, when Bill Gates was interviewed by the Financial Times a few weeks after he published his recent book on the climate challenge, and the journalist asked him, after Bill had sort of pontificated about the climate solution, well, what are you doing, Mr. Gates? And the only answer he gave was, well, I am investing in this remarkable project in Iceland. But the key to this is, in fact, the basalt. The basalt, the form of stone and rocks under the ground. And the extraordinary good news is that this basalt is not just in Iceland. It is in the United States. It is in India. It is in Russia. It is, in fact, in most places around the world. And the characteristics of the basalt as a rock is such that when it touches base with the CO2, it creates a new form of stone, which will store the CO2 forever, forever. And nobody will see it anymore. It's not a junkyard that we will see for centuries to come. No, on the contrary, it will be invisible to the human eye. And as you might remember, 10, 20 years ago, when the scientific and the business community first started talking about storing carbon, the question was, will it escape in the future? How can we make sure it will not sooner or later re-emerge and then threaten the atmosphere? The reason why I am telling you this is that we now have scientifically and technologically proved solution, which is also commercially viable, to take CO2 from the air and pump it into the ground where it touches base with basalt. And because basalt can be found all over the world, as I told you, we can now create a series of what I call pumping stations in the United States, in India, in Russia, and dozens of countries, and reverse the process started by Henry Ford. Instead of pumping petroleum and oil into cars, we pump the CO2 into the ground where it touches base with basalt. What is now needed is to take this forward on a commercial basis, big time, in the next 5, 10, or 15 years. Although we in Iceland can build a terminal, sure, as we will, to demonstrate to the world that this is possible. We are a small country. I have said in recent months, we need the Coca-Cola and the McDonald's business model. We license the technology to any partner, anywhere in the world who want to make profit, enhance their financial position by running such terminals in different parts of the world. So, my dear friends, the good news is we now have the technology to reduce the CO2 which is already in the atmosphere. And unless we do that aggressively, we will never be able to achieve the target of 1.5 degrees. This is the other part of the climate challenge, which unfortunately very little attention has been paid to, because the focus has been primarily on reducing what we put into the air with electric cars and all other measures. So that is why I say to you, in terms of climate restoration, the big challenge now is to create a global system of this reverse pumping, where we return the CO2 to the ground. And we can do it. The science is clear, the technology is clear, the business model is clear. What is needed are entrepreneurial partners in different parts of the world who will make this in a relatively short time a big global business, in the same way as the oil companies, which started small, became big global enterprises. What to me is fascinating is that to save the world from the climate challenge can become an extraordinary profitable business. But people have to realize that the new model actually makes sense. They have to be aware of the technological achievements. And that is why I welcome your agenda here today to talk about climate restoration, because that is the focus we need to keep, not just in the years to come, but here and now and forever. Thank you very much for inviting me to participate in your dialogue. And I will be eagerly waiting to receive the summary of your conclusions.
Thank you, Chairman Grimson. We are so grateful for your keynote address and your presence. And you set the context very well for our next panel, which is commercial climate restoration solutions. And the moderator for this panel is Dr. Erica Dodds, who will introduce the panelists. Let me have the pleasure to introduce Dr. Dodds. Dr. Erica Dodds is the Chief Operating Officer of the Foundation for Climate Restoration, the nonprofit committed to removing the excess carbon from our atmosphere. Erica has presented at the UN headquarters and at the climate convenings across the country.
I think he's putting somebody else on first.
As the Chief Operating Officer of the Foundation for Climate Restoration, Erica is committed to empowering people through engaging with climate. She believes
Speak. Oh, he's taken his. Oh, okay.
was I muted? Oh, I sorry. Okay. Thank you, Chairman Grimson. We are grateful for your keynote. Sorry that I was muted while I was speaking. We move on to our next panel, Commercial Climate Restoration Solution. The moderator of this panel is Dr. Erica Dodds, who will introduce the panelists. Dr. Erica Dodds is the Chief Operating Officer of the Foundation for Climate Restoration, the nonprofit committed to removing the excess carbon from the atmosphere. Erica has presented at the UN headquarters and at climate convenings across the country. As the Chief Operating Officer of the Foundation for Climate Restoration, Erica is committed to empowering people through engaging with climate restoration. She believes that global climate action should focus on restoring our climate to safe and healthy conditions that will safeguard our planet for future generations. Please join me in welcoming Dr. Erica Dodds. Erica, to you.
All right, thank you so much for that introduction, and thank you as well for having me. It's an honor to be here with such incredible speakers and speaking on such an important topic. So thank you again. As Sumitra said, my name is Erica Dodds and I'm the Chief Operating Officer for the Foundation for Climate Restoration. Our work really focuses on what would it take to get to a safe and healthy climate. And it's clear that a lot of the conversation on this subject has really been focused on mitigation, as we just heard from our keynote speaker. One thing that has come up again and again is that there are a lot of really promising solutions for using CO2 as a commercial input instead of simply treating it as a waste product. But this conversation has really not made it to the forefront yet. So I'm very excited to be able to introduce you to this incredible panel of speakers who will give us a brief presentation on this topic, focused on the work that each of them does. And then we'll have some Q&A time at the end. So please do make sure as the speakers are speaking that you're putting any questions that arise into the Q&A box. So first, let me please introduce Dr. Graciela Ciesielnicki, who is the co-founder and CEO of Global Thermostat and co-creator of a carbon removal technology that can reverse climate change. Under her leadership, the company was awarded a silver designation on Pepperdine Graziadio's Business School's 2020 Most Fundable Companies list, and its technology was chosen by MIT Technology Review as one of the 10 breakthrough technologies of 2019, a list curated by Bill Gates. Dr. Ciesielnicki is a professor of economics and mathematical statistics at Columbia University and director of the Columbia Consortium for Risk Management. As a world-renowned economist and environmental scientist, she has made lasting impacts on environmental law by making creating, designing, and writing the carbon market of the United Nations Kyoto Protocol. She also worked as lead US author on the Intergovernmental Panel on Climate Change, which won the Nobel Prize in 2007. Over to you.
Good morning. It's my pleasure to address this group, this audience. I'm looking for the presentation, right, about the future prospects of direct air capture, which is the official name for the carbon negative technology that Global Thermostat has created. I am the CEO and the co-founder of Global Thermostat, and this technology has been identified as the top 10 breakthrough technologies of 2019 in the MIT Technology Review as curated by Bill Gates. I'm trying to, this is why carbon removal, the technology that we're talking about here, is imperative. The science is clear now that to prevent global warming above 2 degrees Celsius, we must remove billions of tons of CO2 that are already in the atmosphere and additionally drastically reduce the ongoing emissions. We need to remove 670 billion tons. It is on average 8 to 10 billion tons every year. So we need urgently a cost-effective, scalable solution to achieve this, to remove CO2 from the atmosphere. The direct air capture solution that we have was created about 10 years ago. Our patented technology is uniquely capable of delivering low-cost CO2 direct air capture. It has 67 patents, and what it does is that zero-cost carbon is obtained directly from the air, and it passes through standard industrial fans into our monolithic contactor. Our honeycomb monolith contactor selectively traps the CO2, and then a low temperature process separates the CO2 and then ejects 98.5 pure CO2 from the monolith. And the heat transfer mechanism regenerates the sample so that the whole process can then start again. The most significant milestones from development starting in 2020 were the award of a Department of Energy funding to develop a prototype with continuous motions. Also in September 2020, expand an agreement with ExxonMobil for the chemical carbon removal technology that we have. In October 2020, Global Thermostat was awarded the most fundable company by Pepperdine Business School. In December 2020, the dedicated process pilot was completed at the Technology Center in Colorado, in Denver, where anybody can go see it. In April 2021, this year, the supply equipment needed to remove atmospheric CO2 was produced and is going to be shipped to the Haru-Oni plant, where, as part of a project with Siemens, is going to join our CO2 from air with hydrogen from water, producing essentially a chemical that is molecule by molecule equivalent, identical to gasoline, but is produced from air and water. In July 2021, Cornetech awarded a DOE funded to further improve Global Thermostat monolith contactor. And in 2021 as well, in July, Black & Veatch was awarded a Department of Energy funding to design a large-scale Global Thermostat direct air capture plant. The commercial advantages are simple. It can be located anywhere, near carbon users or sinks, can be located anywhere because it just needs air. It can reduce or eliminate pipelines. it allows optimal allocation of reduction cost across the economy and can be implemented in countries that have limited carbon emissions. With respect to the market needs, the carbon-based economy refers to the fact that much of today's economy depends on carbon-based products like fuels, fertilizers, food, plastics, chemicals, building materials, all of which are produced with CO2. And in reality, right now, the market for CO2 is 1.1 trillion annually during this decade, including food and beverages, aggregates, polymers, methanol, concrete, and other industries. So this is why what we are producing is simultaneously beneficial commercially and is beneficial for the environment as required by the US National Academy of Sciences and the Intergovernmental Panel of Climate Change to remove the CO2 that is already in the atmosphere, reduce its concentration, we can reverse climate change. This is a very ambitious goal, however, and it's going to take at least a decade.
Thank you so much for that inspiring presentation to kick us off. I am so excited by the opportunity that direct air capture presents and by the leadership of Global Thermostat in that space. Next, we're going to hear from Dr. Brent Constance, who's the founder and chief executive officer of Blue Planet Systems Corporation, an innovative company creating a next generation product using carbonate materials. Dr. Constance is a serial entrepreneur with expertise in biomineralization. Over the past 25 years, as founder and CEO, he's led 3 medical device companies to advance mineralization technologies for orthopedic bone cements. He founded Calera to address global climate concerns with aspirations to permanently sequester gigaton quantities of carbon dioxide in the form of carbonate materials. Dr. Constance received his doctorate in earth sciences at University of California, Santa Cruz in 1986, studied biomineralization as a Fulbright scholar at the Weizmann Institute of Science. And now he'll be speaking to us about his work with Blue Planet Systems. Over to you, Brent.
Great. Thank you very much, Erica. It's really a treat to be here and have a chance to talk to everybody about what we're doing. I'm going to focus on things that can happen in the next decade, because I think everybody knows there's a lot of really exciting things going on in the field now. Some of them are sort of 2040 solutions, 2050, maybe 2070 solutions. So I'm going to talk about something that can happen in the next 5 to 10 years and reach gigaton level. Most of the carbon on Earth actually is sitting in limestone. So I like to bring numbers into these discussions, because often we have a lot of great solutions, but some of them are going to, if they really are netting out carbon, they may take a couple decades to get and employ. But if we look at the Earth today, there's about 70 billion tons or 70 million gigatons of carbon as limestone. So that's most of Earth's carbon. To put that in comparison, the whole atmosphere has about 750 gigatons compared to 70 million gigatons in the lithosphere as rock. Even the hydrosphere, all the ice caps, rivers, oceans, lakes, are about 40,000 gigatons, and the whole biosphere, you know, all the rainforests and everything, you know, the plankton in the oceans account for, you know, about 5,000 gigatons. So limestone is already where most of Earth's carbon is, and it's the skeletal remains of marine organisms who make calcium carbonate skeletons, and then they die and are fossilized and lithified into limestone. That's where limestone comes from. It's important because it's also by mass the largest commodity on Earth. It's already being moved around. All the logistics are already in place. So for example, Blue Planet, my company, makes limestone synthetically in a biomimetic fashion, similar to the way natural limestone forms, and forms a synthetic limestone that can be used in the same way. And limestone is the most common aggregate, meaning sand and gravel, that's used in concrete today. And concrete's the most used building material in the world. So for example, when Blue Planet did Terminal 1 at San Francisco International Airport, our plant simply manufactured the limestone out of CO2. The concrete ready mix company that pours concrete picked it up at the plant, took it to the ready mix plant near the airport, and they poured the concrete. So part of what we need to think about when we're talking about this is, it's one part of it is capturing the CO2, but the other part of it is, what are you going to do with it? And there's a whole bouquet of fabulous applications, but then you have to ask which applications can take gigaton levels of CO2. And there are very few, it turns out. You know, people have to appreciate that 1 megaton or 1 million tons of CO2, it takes 1,000 megatons to make 1 gigaton. And there are hardly any plants today that are even capturing 1 megaton. So we're 1,000 times away from capturing a gigaton, and even further from capturing, say, 20 gigatons, which would be half of everything that humans put out. So if we had plants that were, say, capturing 1 million tons of CO2 a year, you need 1,000 of those, netting out 1 million tons to net out 1 gigaton. So in sort of scanning all the things we could do to take CO2, whether it's coming directly out of the atmosphere or after an industrial emission is mixed with the atmosphere, doesn't really matter. The point is, what are we going to do with it once we've got it? And if we get it via direct air capture, that's great. Now, if we look at the market for rock, it's the largest market in the world. If we look at the consumption of rock, it's not surprising, but it's in the, and this is in billions of tons in the upper left here. Those are 1 billion tons is a gigaton, and you can see, you know, China alone is using 10 gigatons of rock. Now I bring this up because limestone is primarily calcium carbonate, and the molecular weight of calcium carbonate is 100 grams per mole. And in every mole of calcium carbonate, there's 1 mole of CO2, which is 44 grams per mole. So if I have a ton of limestone I've synthesized, I have 440 kilograms of CO2 that's now permanently sequestered in the crystalline state in the limestone. So it's 44% by mass CO2. So you can see, you know, in China's 10 billion tons of limestone, primarily limestone that they're using, you could sequester over 4 gigatons of CO2 in a product that the government's already purchasing and paying for and used. And I think it's important that the economic models are not dependent on government subsidies to have a viable business. I think it's really important that there be a basic fundamental business there. If there are government subsidies, which there aren't in 90% of the world, that's nice, that adds on to it. So worldwide, we estimate that there are about over 50 gigatons of rock mined and moved every year with existing infrastructure. If you take just the state of California, which if it were a country, would be a significant country, we have only a fraction of the rock quarries supplying rock that we need long-term to actually meet our demands for concrete. So we import a lot of rock from British Columbia, for example. And this pattern is all over the world. There's a shortage of rock. You know, we're importing sand into the Middle East because they just have windblown sand and they need water-moved sand, for example. So it's a really interesting market globally. India is out of sand for their concrete, for example. The map of the US in the lower right shows just one particular type of aggregate that is only produced at a few sites around the US. Now, if we look at what are we actually doing, we've built a plant now that's begun to operate on San Francisco Bay. It's at a power plant that puts out between 1 and 2 million tons of CO2 a year. So with 1 or 2 million tons of CO2, with 1 million tons, we can make 2.5 million tons of limestone rock to sell. Now, this plant was 100% financed with debt. And one of the real problems with bringing new technologies out is getting those first plants funded. They call it the Valley of Death because it's very difficult to get investors to show up when it's a brand new technology. In this case, the plant has solid economics. It has a 27% return on investment for the investors. We have a great offtake. In fact, carbon negative concrete is specified now at San Francisco International Airport, and they're pouring millions of tons of CO2. And we're taking this model out with many partnerships around the world. So fundamentally, it's a way that governments can mitigate gigaton levels of CO2 and do it within the next decade with existing infrastructure, creating jobs and prosperity with the money they're already spending. So thank you very much.
Thank you so much, Brent. Last but not least, we'll hear from Dr. Peter Wadhams. Dr. Wadhams is an emeritus professor of ocean physics and head of the Polar Ocean Physics Group in the Department of Applied Mathematics and Theoretical Physicists at the University of Cambridge. He's the UK's most experienced sea ice scientist with 40 years of research in sea ice and ocean processes in the Arctic and the Antarctic. He's led 46 research expeditions to the polar seas and carried out 6 voyages to the North Pole from 1971 to 2007. He was a pioneer in the use of AUVs, autonomous underwater vehicles under sea ice. So Dr. Peter Wadhams, over to you.
Okay, excellent.
Thank you very much. I'm very pleased to be here. And at the moment, I'm not involved in Arctic work since I'm, in fact, in a car driving through the island of Sardinia to a meeting concerned with electric cars. So I've heard really everything that I wanted to say has been already said. So I'll just dot a few I's and cross a few T's. And the first point I want to make is that it's generally agreed we have to take carbon dioxide out of the atmosphere. And the whole thrust of the Intergovernmental Panel on Climate Change is basically wrong in the sense that if they think that we can deal with the temperature change problem simply by reducing our carbon production, then that just simply won't work, because any carbon production leads to an increase in carbon dioxide level and a warming of the climate. So it's generally acknowledged that we have to get rid of the CO2. But when we say, I suppose my first point is that when we say CO2, we really mean all greenhouse gases. So we should be putting as much emphasis on how do we get rid of methane, for instance, from the atmosphere, as how do we get rid of CO2, because methane is coming up very fast as a rival to CO2 in terms of its climatic effect. And the techniques which people have described in this session, which are very successful in getting rid of CO2, are not, there are not such successful techniques around for getting rid of methane. We're still really rooting around at a basic research level to find methods that will enable us to get rid of either methane from the normal level in the atmosphere, or methane from potential outbreaks of it, for instance, from the Arctic seabed. So we've got a methane removal problem that's not solved in the same way as the carbon dioxide removal problem is. Then we heard from His Excellency Grimson about CarbFix and Climeworks and what is in fact a wonderful discovery that that carbon dioxide removed from the atmosphere can react with basalt in very many potential places on the planet and be turned into rock where it's permanently disposed of. And this is wonderful, and it means we're putting carbon dioxide into an inaccessible place. This is fine for many people, but for some people, or many other people, they would like to see the carbon dioxide put to some good use or some profitable use, and turning into rock and disposing of it forever is not a profitable use. So we've heard from both from the Climate Global Thermostat and from Blue Planet, especially in the talk by Brett, that we can turn it effectively into limestone or into some other product which we require a lot of. And he rightly says that is probably sand or cement, because there are not many products that the world needs about 50 gigatons of per year, and really sand and cement is about it. And so he's wise in making that the emphasis of Blue Planet's effort. Let's produce something that we have an endless need for. So the only thing that to add there is, and this I think arises from discussion I had with Brent several months ago, which was, well, is it possible to take the carbon dioxide out of the ocean rather than out of the atmosphere? Everybody, when they think about carbon dioxide removal, thinks about removal from the air. But there have been techniques proposed, including cultivation of kelp, which grows very, very fast, to remove carbon dioxide from the ocean. And the principle is, of course, that carbon dioxide removed from the ocean is equivalent to carbon dioxide removed from the air, because the carbon dioxide rebalances itself between ocean and atmosphere. And although it seems obvious that if we want to get rid of CO2 from the atmosphere, we should take it out of the atmosphere, that doesn't necessarily follow. It may be that it does when we look at the economics, but it is worth still looking at the various ideas that have been proposed for oceanic removal of CO2. So those were really the main points I simply wanted to add, except to say that if you start looking at comments by politicians on CO2 removal, there was a huge surge of interest and approval for getting carbon dioxide out of the atmosphere by direct air capture, that this seemed to be the solution. But the politicians seemed to go a little bit cooler when they learnt of the cost. And it is probably the case that the costs of CO2 removal from the atmosphere are very, very high. At the moment, this may not continue to be the case, because the cost of generating solar energy was enormous 10 years ago, and now it's very low. You can do, with technology, you can do a lot. One of the main things you can do with technology and engineering is to make processes cheaper. and significantly cheaper. So I think we can be hopeful if enough money is spent and enough ingenuity is applied to be able to find ways of taking CO2 out of the atmosphere much more cheaply than we can now, let alone the additional benefit that we get from putting the CO2 to use, as in the case of limestone. So
Great.
I think we need to keep very much at this problem, and I'm lost in admiration for all the people who are doing this, because it's a really important thing for the human race that we should be able to do this, given that we can't expect to get out of our climate crisis by reducing our emissions. That's a kind of fantasy. The reality is we've got to buckle down and find a way to get rid of CO2 from the atmosphere.
Great. Thank you so much, Dr. Wadhams. That was really well said. We're going to move into Q&A now. We've received a lot of excellent questions from the audience, so I'm going to go through in the same order to start out. So the first question is for Graciela. Does direct air capture require energy? How do you ensure that with the energy requirements, the process is still net carbon negative?
So far, we have been using clean energy sources that don't emit CO2. As pointed out by Dr. Wadhams, the lowest cost of electricity now is solar, is photovoltaic solar plant. It's about $1.50 per kilowatt hour, which is lower than the cost of electricity produced from all fossil fuels, for the reasons that he explained. So it is possible to use low-cost electricity that produces no CO2 emissions. It's also possible to do it with wind. And therefore, just by using those simple facts and the fact that the solar revolution has completed, and now our lowest source of electricity is solar, and it comes directly from the sun as it should, without intermediaries, we can be assured that any power that we use is non-polluting.
Excellent. That's great to hear. Next question is for Brent. How rich, how pure does your CO2 input stream have to be? Obviously, a power plant exhaust works, but what's the minimum CO2 concentration needed?
Yeah, so one fundamental difference about what we're doing is we're following what we call a biomimetic process, similar to the way natural limestone forms. And like I said, natural limestone is the skeletal remains of corals and other calcium carbonate forming organisms. And pure CO2 actually doesn't exist on Earth, except in a few chemical places like Praxair and Air Products places, or where we're trying to compress it and liquefy it. And we don't go through any step where we're concentrating pure CO2. So the actual concentration, whether it's from a cement plant that's 300,000 parts per million, or a natural gas-fired power plant that's 50,000 parts per million, or the atmosphere within half a mile of a power plant, which is more like 1,000 parts per million, or the top of Mauna Loa, which is 400 parts per million. All we're doing is converting it into carbonate and then precipitating calcium carbonate. So there's some economies of scale when it's more concentrated, but there's some disadvantages to more concentrated as well when you're doing what we're doing.
That's really helpful. Thank you. Next question is for Peter Wadhams. Do you think that oceanic methods like kelp cultivation, as you mentioned, can rival direct air capture economically?
Yes, I think it can. There's been a wide variety again of oceanic methods proposed, but it seems to me that the kind of a brute force method of growing kelp and then destroying it or removing it is the cheapest and most effective. There are techniques that have been developed, in fact, at my current university, at Turin Polytechnic, for remediation of water, that is producing phytoplankton especially diatoms, by some targeted nutrients. The diatoms then grow and die, fall to the seabed, and that's a way of reducing CO2. But it's quite slow, and also can go wrong because you might be targeting the wrong diatom with the wrong nutrient. And they're doing experiments in the Polytechnic to make sure that you can do the right thing, but it's not as resilient and brutal a method as just growing kelp. So I would say that there may be methods, and they deserve to be looked at just because it's a way of getting carbon out of the Earth's climate system that could be potentially more economic than removing them from the atmosphere, but probably in the end won't.
Looks like we've lost Peter Wadhams for the moment, so we can move on to the next question for now. Do we have, between Brent and Graciela, do either of you have an estimate of how much CO2 is currently being removed using technological methods on a yearly basis?
The amount of CO2 that is being removed from direct air capture is relatively small, relatively very small as of now. But in the next 10 years, we hope it will be possible to remove 1 gigaton, perhaps. And we have agreements with big companies who try to do exactly that, working with Siemens, working with Exxon, etc. But it's not at present. I am sorry, I didn't mean to interrupt Brent, because what Brent said is true, that rocks or aggregate is perhaps the largest source of CO2 removal.
Brent, would you like to add anything?
Well, the plant we just built is it's only going to do 15,000 tons of CO2. And the one we're building will do 170,000 tons a year. And then we'll be aiming at 500,000 tons per year next. But, you know, we've signed about 7 very large corporate partnerships with emitters who will be replicating this in the hundreds of plants over the next decade. So, you know, there's a chance just Blue Planet could get to a gigaton, you know, by 2030. And it's very easy to imagine that.
Excellent. That's very exciting to hear. Okay, we just have a couple minutes left, so I'd like to do a quick speed round with all of you, starting with Graciela. If you had a magic wand and you could make one change in the world to promote large-scale carbon dioxide removal, what would you do?
I would complete the proposal currently made by me to upgrade the European Union emission trading system, which is the carbon market of the Kyoto Protocol that I wrote in the Kyoto Protocol, into a carbon removal market, because that's likely to bring a lot of funding. And I will introduce financial instruments that are similar to mortgage-backed securities, and that, but they are securities backed by offsets of CO2 that would be enormously mobilizing of resources for this.
Did you finish your thought there?
Sorry?
Did you finish your thought?
Well, maybe, I don't know what you
Okay.
heard.
I think we heard to the end. So thank you. That's very helpful. I think that's a great idea.
The European Union carbon removal market, as opposed to carbon emissions, carbon removal, and it's possible to do it right now. And we need to introduce financial instruments that have the scope and the attractiveness of mortgage-backed securities. But instead of being securities backed by mortgages, security backed by offtakes of CO2, that will create an enormous liquidity where governments can buy some of those securities and the public will trade them. And you're talking trillions of dollars that would go towards that area of removal of CO2.
Excellent. Great answer. Thank you. Brent, same question. If you had a magic wand to promote large-scale CDR, what would you do?
I think governments need to use their purchasing power more so than maybe their taxation or other powers. Something every government in the world does is fund very large infrastructure projects. Over 45% of all the concrete that's purchased in the world is paid for by governments. And so governments have this enormous procurement power that they're not using, and it's difficult. In California, we have this buy clean legislation that we've been trying to get through. And it's been difficult, and they're trying in New York and New Jersey. But that's where actually a lot of capital is in funding of infrastructure, and if that can be directed toward, like making aggregate and sand for all those projects, that would be, trillions of dollars that are going to mitigation from even the poorest countries in the world, right? Because even the poorest country in the world is building roads and dams and other infrastructure. And all they have to do is use the power of the pen to have a procurement preference. And that would create the whole market and drive it right through.
All right. Thanks, Brent. Thanks, Graziella. And thank you again also to Peter Wadhams, who it looks like has lost his connection. That brings us just past the end of our time. Thanks for sticking with us. I know I've learned so much this session, and I hope you all have too. Thanks for the brilliant questions that you've asked our speakers. And back to Sumitra. Thanks.
Thank you, Erica. Thank you, our panelists. We are very grateful to the speakers for facilitating a great discussion today. Thank you. Now we move on to our next panel, and we already heard how ocean can play a huge role in climate restoration. So our next session is on restoration of oceans and the cryosphere. The moderator for the panel is Jeremy Douglas, who will introduce the panelists. Let me have the pleasure to introduce Jeremy Douglas. Jeremy Douglas is an executive vice president at Oceanwide, a global conservation organization that inspires millions of people to take action to improve the health of our oceans. He leads communications, strategic partnerships, fund development, and government relations at Oceanwide. He is passionate about collaborative and creative ideas to drive positive change. Please join me in welcoming Jeremy Douglas. To you, Jeremy.
Okay, thanks so much, Sumitra. I'm trying to get my video on here. Does anyone have the reins on video? Otherwise, I'm just a voice floating out there, but hopefully we'll be able to get the video so you can see what I look like. I'm not, there we go. Thank you. Sumitra, I don't remember what it looks like to see someone in a tie and a suit. So used to being on Zoom calls these days. So I even had to find out where I keep my colored shirts. So nice to be part of this discussion. I'm really looking forward to it. As you mentioned, I'm Executive Vice President for External Relations at Oceanwide, and I'm coming to you from the traditional unceded territory of the Coast Salish people, the Musqueam, Squamish, and Tsleil-Waututh, also known as Vancouver in Canada. So very happy to be here and help moderate this panel. Looks like it's going to be an amazing discussion. We've got Dr. Leslie Field, the founder and CTO of the Arctic Ice Project, Dr. Brian von Herzen he's the director of the Climate Foundation, and then Paul Dobbins, the senior director of impact investments at World Wildlife Fund, WWF. So 3 fantastic speakers, a topic that is obviously near and dear to my heart and to Oceanwise is, as our name implies, oceans is kind of the thing that we're focused on as an NGO, like some of the panelists. And we're looking at how we can inspire optimism, how we can inspire action, concrete actions and solutions, I think like the panel members, to drive change that's going to help tackle the climate crisis. And we look at how we can do that from a range of different solutions, and including using kelp and something we call seaforestation to draw down carbon by having more kelp restoration. So very excited to hear the solutions the others are going to bring forward. So the way that this is going to work, we're going to hear from each speaker about a 6-minute presentation. I think some of them have slides. Then I'll ask a question to stimulate some discussion, and then we'll open it up for Q&A at the end for about 20 minutes or so. But feel free to put in the chat any questions that you have in the meantime. So with that, I'm going to start in the order of Dr. Field, and then Dr. von Herzen, and then Mr. Dobbins. So I will start with Leslie. If you are ready to go there, Leslie, then I'll hand it over to you.
Sure. Thank you very much. I'm quite honored to be in this company, right? This was the initial speakers have been absolutely inspiring, and I'm looking forward to sharing my work. So here I go, sharing screen, hoping all works. Okay. Can you see it? Okay, I think you can. Great. I have about 30 seconds per slide, so I'm going to speak quickly because there's a lot to say. I'm Leslie Field. I'm the founder and CTO of Arctic Ice Project, originally Ice 911 Research. We work on climate restoration, specifically restoration of Arctic ice, which really plays into both restoration of oceans in the cryosphere. I like to say time to act because it is high time to act, but this also gives the world a little more time to complete that transition to sustainable fuels and energy solutions as well. We're trying to slow down some of the risks. What do we mean? I often show this whole beautiful NASA video, which you can find on our website and elsewhere, showing the decline of brightness in the Arctic, the decline of albedo over the last few decades. This has been a very large change to the planet's ecology, basically, to our climate system. We've gone in just a few decades from having a substantial area of bright reflective ice in the summer to reflect away sunlight to a much smaller amount. It's been a relentless decline. Peter Wadhams, who you just heard from, says in his book, Farewell to Ice, that this is adding as much as 50% to the direct global heating effect of CO2 if you add up the ice and snow, which is really pretty amazing. And then Dr. Don Perovich, another eminent ice expert from the US, gives the report card on how much of this inventory of ice is left. And a couple years ago, it was from 30% we had of Arctic sea ice cover being this reflective stuff to down to about 1%. So it's accelerating climate change and climate change risks, and that's not good. In fact, the situation keeps getting worse and worse, as I'm sure you're all aware. The American Meteorological Society was just surveying how much worse it's gotten in 2020. There were $22 billion disasters in the US. The previous record was 16, 2011 and 2017 had died. Since 2016, in just one country, the US, the cost, so over these 5 years, the cost of billion-dollar disasters in the US was more than $600 billion. And I live in wildfire territory, so I'm feeling it personally here. So there's no argument that it's urgent to do something. And there's also no argument that a lot of money is already being spent or lost by not doing something. So this is something I think worth bringing up. What's our proposed solution? It's a material, basically I did a search for materials of how could we replace that lost reflectivity in a safe way. That was really the idea, safe, localized, surface way. And our favorite material right now is hollow glass microspheres. They're these little sort of white sand-like things made of silica, chosen to be an intentionally safe natural material. These are engineered, these hollow glass microspheres. They're a thin shell of silica glass around a gas core. But silica is so ubiquitous in our ecosystems that we've all basically evolved with this sort of thing. And so it's not a kind of plastic. It doesn't bind with oil-based pollutants. It's passed all the safety tests so far. But our first principle is we don't want to make anything worse. And so first do no harm is the guiding principle. So this is what we've been working on for quite a while. We've tried a variety of materials to start with, but this is holding up as a good one. If you want to make an intervention, right, an intentional change to climate, there's really a lot to consider. And I just want to show that we are looking at all of these kinds of aspects. What's the effectiveness? How safe is it? What would it take to adopt it? Are we actually solving the problems people have? That's incredibly important. Are we working and learning from all the other big organizations out there? And can we get a framework, a safe framework for understanding and implementing the safest and most effective of these solutions in time? We do a lot. This is a lot of our work: researching, lab testing, deployment research, climate modeling. Basically, a thin layer of this material, about 500 microns thick, maybe a little bit more, of a few layers of these very small grains is enough to boost reflectivity. Open ocean has almost no reflectivity, right? 5% or so reflected. Young ice has a little. You've seen it in that map. You've got some, but you've only got a little reflectivity. Thick ice and snow, what we've mostly lost in Arctic sea ice, reflects a whole lot. And if we put a thin layer of this on top of young ice, it instantly acts more like that multi-year ice. Not all the way. This is all a light touch solution. Make some small adjustments to have the biggest impact we can. You can see bare ice, pretty dark. This is on a test pond we use a lot in Minnesota. This is snow. You know, bare ice is much less bright than snow. This is what that same patch of bare ice looks like as soon as we put the hollow glass microspheres on. So the nice thing about this is it's an instant change in reflectivity. And that's a big deal. We don't have a lot of time to wait. This is what it looks like on that pond in Minnesota. This is our test site up in Utqiagvik, Alaska, where we've done a lot of testing over time. Everything that we've done so far says it's safe, but we've got farther to go. And we're really, really excited to be finally having rounded up the funding to be able to start this wonderful evaluation by Sintef Ocean in Norway, who is going to be looking at, this is a group of, a very august group of biologists who understand, marine biologists who understand a lot of the skills that we don't have, right? We don't have every skill in the world. We need collaborations like this. And we're just starting it. The hypothesis is that hollow glass microspheres, these sand-like, floating white sand-like materials, is environmentally safe, an environmentally safe method to restore ice. And they have a wonderful plan and some wonderful test facilities. We've been developing the plans together, and we'll see. So we need expert outside review. So far, so good. We're going to see what they say. You also need, when you're doing these tests on a small scale in a pond, you want to see, you know, what does that mean to the world? And so we've been partnering with Climeformatics, which is an expert climate modeling, again, small group, but expert, to show what are the impacts if we deploy in the Fram Strait, where we've had a lot of ice export over time, or in the Beaufort Gyre, the historic nursery for multi-year ice, which could have effects of helping to preserve permafrost inventories, for instance, from melting. The idea is we want leveraged areas. It's all about leverage, so we make a minimal intervention for a maximal benefit. And the idea is we don't need or want to carpet the Arctic. We want it sort of small. We also are looking at, started actually by Shamitra inviting us to talk about Himalayan ice melt, and continued with the urgency of Greenland ice melt, an area in which H.E. Grimson, who spoke first in this session, is very interested. if we can slow Himalayan and Greenland ice melt, we can help preserve water supplies for 1.6 to 1.7 billion people. That's a big deal. That is a humanitarian crisis that is already underway. And we can reduce sea level rise potentially for coastal communities. Additionally, right, as you've heard, we could also, by preserving Arctic ice, reduce this horrible methane emission risk in the Arctic. So, could glacial ice loss be slowed by modifying the reflectivity of glacial ice surface and meltwater? And we've got indications already that that is in fact the case. We've got some, I've got a data slide later if you wanted to see it, but it's really important, and we're really excited to get this started. Basically, in summary, in conclusion, we're working on restoring oceans and the cryosphere, and it really is the time to act. More and more people are acknowledging in peer-reviewed papers that this is perhaps the last decade we have in which to make a significant enough difference to really have reasonable lives for our children and their children. And we need to build collaborations like that one with SINTEF and the climate modelers and such in order to accelerate the work and get the job done in time. Thank you very much. I look forward to the questions.
Thank you, Leslie. That is fascinating. I love these practical solutions because, you know, as you say, it's time to move from talk and research to like, okay, what are some actual solutions we're going to put in place there? And especially for the Arctic, which for, as you know, the Inuit communities living there are already in a 2-degree world. So it's not something in the future they're dealing with loss of sea ice and what that means for food and for travel and everything right now. So well done on this.
Thank you so much. I will say, you know, it is ground zero for climate change, right? It's 3 times accelerating temperature rise, 3 times as fast as elsewhere on the planet.
Yeah, absolutely. And that's what we work in the Arctic with Inuit communities and can know firsthand as well what they're dealing with. And I think for a lot of people that's out of sight, out of mind. So glad to see that you're focusing on that. And also the intersectionality between addressing climate change and addressing ice and water sources and the health impacts that has for communities throughout the world. So that a good effort there as well. Excellent. So looking forward to now Dr. von Herzen, am I pronouncing that correct? Von Herzen, presentation from Executive Director of the Climate Foundation. So I will hand it over to you, Brian.
Thank you, Jeremy. Pleasure seeing you today and a pleasure speaking here at this august group. Very happy to describe for you the work that we're doing here at the Climate Foundation. Let me know if you're seeing our slides okay, and I'll proceed accordingly. Good. All right. Assuming it looks good, that's great. So we're with the Climate Foundation. We're very happy to have our work supported and articulated in the Drawdown book and Regeneration by Paul Hawken, as well as the film 2040. At the Climate Foundation, we focus on regenerating food security for billions of people who depend upon the oceans, enough food not only for humanity, but also for nature and those marine ecosystems, and finally being able to measure the carbon export of these regenerative interventions. Today, we're dealing with a precarious and dangerous situation. 93% of the heat captured by global warming and the greenhouse gases ends up in the upper ocean, and that upper ocean is on the front lines of climate disruption. It's pretty amazing that without the oceans absorbing carbon from the atmosphere, we would have 50% more anthropogenic carbon in the atmosphere today than we would otherwise. You know, without the oceans, we would have 50% more than we do today, and that's really significant. So the oceans have really given us about a 30% discount on all the carbon that we've emitted industrially. And the oceans store around 45 times as much carbon as the entire atmosphere. So if you took all the carbon out of the atmosphere and distributed it uniformly throughout the oceans, it would change the concentration of carbon dioxide by around 2.5%. So it's the problem of carbon in the oceans is one of distribution, as opposed to being one of the total amount of carbon in the oceans. And truly getting that carbon back into the middle and deep ocean from whence much of it came is a big opportunity. Now, a paper in Nature Climate Change came out just about 12 months ago, that articulated that this warming that's going into the oceans is actually contributing to stratification. And what does that mean? The red zones are areas where there's less natural upwelling today than there was pre-industrially. And in the last century, we've seen multiple decimations of kelp forests and other macroalgae as a result of this reduction in natural upwelling, to the point where in the tropics, we've seen 60% losses of production in countries like Indonesia and the Philippines during marine heat waves. And furthermore, the California kelp off the Northern California coast, the Nerecistus kelp, has actually diminished by over 90%, as has the Macrocystis kelp forests of Eastern Tasmania and the Eclonia kelp forests of Western Australia. So it's a major concern, the fact that we're losing thousands of square kilometers of kelp forest in the last decade or three. Turns out algae beds and reefs are really good at fixing carbon. In fact, 15% more carbon than even the Amazon tropical rainforest. So in many ways, the tropical rainforests that are carbon fixers of, let's say, California, can be measured by the kelp forest that's offshore. What if we could take the giant ocean area that's shown in the upper left here and multiply it by the high carbon fixation rate of algae beds and reefs to produce some really significant percentages of Earth's net primary production and fix more carbon than we could otherwise? That's what we're asking with marine permaculture, which effectively regenerates kelp forests offshore by providing substrate and deep water irrigation, and brings back to life those kelp forest ecosystem services offshore that can provide habitat for fishes like sardines and anchovies, and provide essential ecosystem services for sea mammals, for seabirds, and for entire marine ecosystems. That's the opportunity that we see with marine permaculture to effectively regenerate kelp forests offshore using floating platforms and submerged platforms. Those ecosystem services can regenerate fisheries, provide food, feed, and fertilizer for our agriculture on land, and sink residual carbon to the middle and deep sea, where if it goes down below 300 or 1,000 meters, it can actually remain for hundreds to thousands of years, respectively. We found over a dozen value chains for the products coming from marine permaculture, beginning with food, feed, and fertilizer. And we have examples of at-sea harvesters and at-sea biorefineries that have actually historically done a great job of enabling at-sea processing and minimal carbon additionality to actually process these materials and get them to shore. In fact, our team in the Philippines is already producing biostimulants that have resulted in amazing agricultural changes. We've seen up to 30% taller rice just in this year in some of the islands that are growing rice in the Philippines, to the point where this intervention alone should enable food sovereignty for countries like the Philippines that do not have it today with respect to having to import rice. And so we're seeing a great opportunity to transform agriculture of many or most flowering plants, including row crops from the US to Europe to Australasia. These biostimulant interventions can have a transformative effect on food security in a climate disrupted world. And then furthermore, it's able to sink huge amounts of carbon. We're estimating up to 7,000 tons of carbon dioxide equivalent coming from just 1 square kilometer of marine permaculture. That, combined with the fact that we can get the same yields on agriculture with 2,100 tons of reduction, let's say 20% reduction in NPK fertilizer use, because these plant biostimulants actually improve the uptake of nitrogen and other fertilizers in the plants. So 20% less fertilizer produces the same crop yield, and that enables another 2,000 tons of carbon equivalent per square kilometer of marine permaculture. And then furthermore, that reduced nitrate applied to the soil produces less nitrous oxides, which has a 300x multiplier on the greenhouse gas multiplier over carbon dioxide. And so we're avoiding another 1,800 tons of CO2 equivalent emissions based on the reduction of nitrous oxide that's produced from those same soils. At the same time, the seaweed that is sunk below 300 meters has a residence time of over a century. And when it gets below 1,000 meters, it can actually have a residence time of more than 1,000 years before that water is again upwelled to the surface. So it presents a blue carbon sink of enormous proportions. Finally, we've demonstrated already 100 square meter platforms that have really demonstrated the incredible biological results with over 100% growth per month. And we're working with new seaweeds with even faster growth rates. It's a real cornucopia of production with thousands of sardines, hundreds of tuna fish, dozens of dolphins, and we even had a whale shark come and spend 3 days with us around this platform. So it's truly, nature's voted with her fins. She has said that marine permaculture is a great place to be, and we're looking forward to enabling this future around the world, offshore in exclusive economic zone waters, and look forward to your questions on this panel. We are running a crowdfunder right now that is going to enable us to grow the next 1,000 square meters of marine permaculture in the Pacific Ocean, and check it out at climatefoundation.org. Thank you very much.
Oh, shameless plug at the end there, Brian. I like it. Wow, you packed so much good stuff in there that I would love to nerd out with you on. As you can see, kelp is something that we love, and I think the world's got to wake up to the potential for kelp. Is just so amazing. Such a cool plant that grows 30 times faster than any, well, some of them 30 times faster than any plant on Earth. So much great stuff in there. Look forward to the questions on that one. And the potential for nature-based solutions in the ocean. I think there's been so much discussion around planting trees on land, which is, of course, really important, but the ocean's 70% of our planet, and we're not maximizing the opportunities there. So great stuff there, Brian. Okay, Paul from WWF International. Never heard of them. Some small NGO, I think. So we'll hand it over to you, Paul. So take it away.
All right, let me know when you're able to see the slideshow here. Let me put it into slideshow view. All right, did that come up?
Perfect.
Okay, wonderful. Thank you, Jeremy, and thank you to the Wharton alumni for this opportunity to talk about our work in seaweed. So World Wildlife Fund, as Jeremy alluded to, is a 60-year-old environmental conservation organization with over 6,000 employees. We operate in 100 countries, and we have a number of practices that we focus on. And I happen to sit in the food practice, and we have identified seaweed farming as a food production system that can provide benefits for both the climate and society. And I think Brian did an excellent job of outlining all of those benefits that we could realize if we expanded seaweed farming. So one of our goals at World Wildlife Fund is to expand or advance seaweed farming, and we're focusing primarily in the high latitudes. So the North Atlantic Rim, the Eastern, North, and Pacific Rim. At this point, we'll go down and focus more in South America and Africa. We're focusing on these areas because they're principally an undeveloped seaweed farming regions. And so we did a landscape scan over 2 years to determine where we could be most useful in helping this industry to move forward. And I'm going to talk a little bit about what we found and why we're focused on it. So seaweed farming has been in practice. The oldest continuously operating seaweed farm is 351 years old this year. It's located in Tokyo Bay. And in 2018, the harvest of farmed seaweed was about 35 million metric tons. If seaweed continues to grow at its current CAGR of 8%, by 2051, it will surpass potatoes as the 4th largest cultivated crop in the world. And I see Brian nodding and Jeremy. We in the seaweed world know this, but if you haven't spent time in the seaweed world, that's quite shocking. And part of the reason is that there are about 8 countries located in Asia that make up well over 90% of this harvest and this practice of farming seaweed in the ocean. And it happens underwater, so it's difficult to see. So unless you're a diver or have access to underwater photography, it's not something that the average US citizen experiences. The seaweed on the right there is called Laminaria japonicus. It's a brown seaweed. The browns are more commonly known as kelps. And we're focusing on the kelps as a family of seaweeds right now for our work. sugar kelp, which is a seaweed that is grown out in the Aleutians and all the way over to Brittany and the high latitudes of the Pacific and the Atlantic, is a relatively resource free production system in creating protein. And if you look at this relative to beef, pork, poultry, salmon, shellfish, other cultivated sources of protein, you can see that seaweed ranks right up there with, from an environmental standpoint, as being the protein of choice if we're able to grow enough of it. This graph was created by Scott Lindell at Woods Hole Oceanographic Institute, who's doing a significant amount of work in better understanding where seaweed fits in the world food supply chain relative to these other production systems as a means of highlighting the opportunity that we have out there for us. As Brian talked about, seaweed is operates like a green plant when it's mature. The kelps, they absorb CO2, phosphorus, nitrogen, three things we have too much of in our oceans in many areas, and they give off oxygen. And while they're doing so, they're creating a highly nutritious food source without any arable land, freshwater, fertilizers, or pesticides. Really a lot of the genius of the and in seaweed farming as a food production system. However, there are significant barriers to advancement, particularly in the underdeveloped world of seaweed farming, where there are higher costs of operation. So one area that we've identified is innovation that will enable these companies to operate in a cost environment that is higher than the Asian countries are operating in. The Asian countries have been doing it for a long time. They've reached economies of scale, and they've focused in on reducing their costs dramatically. And they also have lower labor costs. So there's going to need to be innovation that's going to enable countries in the underdeveloped world of seaweed farming to move forward. And to get that innovation, you're going to need access to capital. The second barrier is social license to operate. All of this happens in the ocean. The ocean is the commonwealth, and so society needs to provide social license for seaweed farmers to get out into the water and actually operate. In the seaweed farming countries, this is relatively easy to achieve. In the developing area of seaweed farming, it can be difficult. Sometimes it can take 3 years to get a decision, and sometimes that decision is no, you're not allowed to do it. And so that's a significant barrier right now. And then markets, we saw, it's really a remarkable CAGR, but if we're going to significantly advance seaweed farming, we're going to have to grow those markets at a faster rate. And then in the middle, it's not something you hear often from environmental organizations, but the most important sustainability metric for all of this is profit. For these things to happen in the ocean, it's going to take for-profit companies to be involved, and they're going to have to make a profit if they're going to be sustainable. And so we're focusing on these three barriers and with an aim to helping companies create profitability in this space, because we think in the long term that will drive advancement of the industry faster than anything else. One area where we have started to make equity investments is in seaweed farms. We own part of a seaweed farm up in the Faroes, which sit halfway between, say, Iceland and Norway. It's an island archipelago. Over 50% of their GDP comes from fisheries or fish farming. And they now have the largest seaweed farm in the North Atlantic. It has about 25 miles of line out. And they've recently launched the first purpose-built seaweed farming vessel in the North Atlantic on either side, Western or Eastern. And they were able to do this because they've been able to attract significant investment. And we see that in the European side of the Atlantic. Over the last 10 years, there's been about 69 million euros invested in small startup companies in seaweed farming. And the pace of investment is accelerating. Just in the last 20 months, 31 million of that 69 million euros was invested in these small companies that are pioneering seaweed farming in the underdeveloped regions of the Atlantic. Social license, very, very difficult to achieve. This is Karen Cooper. She's the first commercial fisher to farm seaweed in the US. And down in the lower right, you'll see one of her buoys. Her entire farm was shot out 3 days after it was put in the water. And it was shot out by other fishermen. There's a significant challenge in social license, not only in the rules and regulations and the bureaucracy that people kind of complain about, saying, it's tough to get in the water, but there's also this cultural side of social license, and that needs to be addressed. What has historically happened on a bay? What should happen in a bay according to the community that has the highest stakes in the health and welfare of that bay? And so we're working on strategies to improve social license through education and communication and dialogue in coastal communities. And you see this playing out generationally. On the left is a lobsterman from Maine that I know. He fished the bay that I used to farm seaweed in, and he is against seaweed farming. He believes that it will impinge upon his ability to earn a livelihood. The young gentleman on the right is someone who would love to lobster, but he can't get a permit to do it. They take over, in some cases, you have to wait almost 20 years before you're able to achieve a permit because it's a closed fishery. So he is seaweed farming as a means to get out on the water and continue his family's multi-generational historical means of earning a living, which is to work on the water. And then finally, markets. You may have heard that cows burp methane, and that there are companies out there that are exploring the opportunity to reduce enteric methane production in the rumen through using seaweed as a feed additive or amendment. And the research here is very, very promising, but it is still early days. And what we're hoping to see over the next 10 years out of the fruits of this research is that it is a viable solution, that it does generate profit for the farmer, and it provides for a healthier, more productive animal, and it improves the environment. It's going to take a lot more research, I think, than what we currently led to believe in the popular press, but the early research is very promising. And so with that, I'll finish up, and hope you join me in helping all of us kelp the earth. Thank you.
Love it, love it. And I hope everyone who's joining is now converted seaweed advocate and a kelp advocate. There's so many great stats, as Brian and Paul especially know. Another one that I remember hearing about is kelp being used in insulation as a way to, not permanently, but for long-term, you can embed and capture carbon there.
Well, products. It's interesting you say that. I grew up in a house that was built in 1695 on Nantucket. And whenever we did renovations on the house and opened up the walls, filled with seaweed.
There you go.
Yeah.
You can eat it. You can eat it too.
After that amount of time, I don't think I'm going to be chewing on it, but not uncommon in old coastal communities.
Yeah, excellent. And this, I think, is a good segue to a question maybe I'll kick off with for each of you. We've got 10 minutes to wrap this up, so just kindly ask that you provide as brief and punchy of answers as you can. But maybe I'll start with Leslie, and we'll go in the same order of speaking. So Leslie, then Brian, then Paul. How do you scale this solution? What is needed to scale that so that it can have real impact for the scale of the climate challenge that we're facing?
Yeah, it's an excellent question. And it's what the climate modeling tries to help us with, is where can we do a leveraged deployment to make things really have a beyond the immediate application area impact. We think it's by selecting the locations properly. But how do we get beyond a small, like 60-foot by 30-foot pond test out? We have been studying deployment methods, and we've deployed 2 football fields worth. So that's what we've done up with very labor intensive methods, right? Dragging between a drop spreader, agricultural drop spreader. We think in truth, what we'll be needing to do is for sea ice, using an Arctic vessel, perhaps blowing the material across young thin ice, at the right time. That might have to be assisted by drones to get things exactly where we need them. On land ice, at least for the initial tests that we would like to show to see whether we can address the various kinds of darkening mechanisms in Greenland, for instance. It's again going to be small tests to start with, but the deployment methods probably include things like drones or things like some machinery spreading. But you've got to choose your areas. What is in the most need? What's the darkest? What's the most impactful as far as helping with currents and such? Could we put it on ice as it's freezing up in the winter and have it immobilize itself there and incorporate right into the forming ice? These are still questions that we've got to urgently complete our research on. But yeah, it's very much on our minds. How do we do this at the scale that matters? Thank you.
Absolutely. Thanks, Elsa. Brian, over to you.
Sure. Could you repeat the question, please?
How would you scale your solution so that it can have significant impact on reducing carbon emissions?
Definitely, thanks. We last year validated the biological response of seaweeds to deep water irrigation, and we got more than 100% growth rate with our red seaweeds in the Philippines compared to the baseline controls that were actually shrinking. Furthermore, our work with the University of Tasmania in the high nutrient zones last year demonstrated 4 times the linear growth rate of these giant kelps depicted behind me. And that was more than 10 meters of growth near fish pens. That was in 12 months compared to the controls that only grew 2.5 meters. So that was 4 times the linear growth rate and maybe 10 times the biomass in the higher nutrient zone as a proxy for deep water irrigation. So at this point, we have already built the 100 square meter platform. We're fundraising now with our dollar for dollar matched crowdfunder to build the 1,000 square meter platform. If we hit our goal this quarter, we'll be deploying that in the water first half of next year. And with that in place, that'll give us the key performance scalings that we'll need in order to finance the economically sustainable hectare. And with that in place, whether it is tropical red seaweeds or temperate kelps, we'll be able to ensure year-round production, where we're looking at 4 to 8 harvests of seaweed per year on these platforms that have replete sunlight, but still need replete nutrients year-round. And those nutrients are available just a few hundred meters below the surface. So we go offshore where there's less contention for resources. That's the great thing. When you're 100 kilometers offshore, you don't have fishermen shooting out your buoys. And so by reducing the shoreline contention, we can eliminate that problem and utilize just a tiny bit of what David Attenborough calls mostly empty ocean to actually regenerate those ecosystem services and get life back on track in the ocean.
Thank you, Brian. Over to you, Paul.
Seaweed farming is already scaled in many of the Asian countries. So there is a roadmap on how to do it. For the underdeveloped regions of seaweed farming that have great potential because of the immense size of the ocean. And, I agree with Brian on David Attenborough's quote, it's fabulous. The money is on the sidelines, it's waiting. Some of it has already started to wade in, but there's a lot of financing out there that's available. The markets are developing, and it's rare you find a market that's over 70 years old with an 8% CAGR and increasing. They think it's going to go to double digit within several years. And so really what it comes down to, it's not the markets, it's not necessarily the technology, because that's being developed. You've heard from Brian some of the amazing stuff that's being developed. It's societal's will. We don't have in the US rules and regulations that would enable this type of activity out on the ocean in federal waters offshore, whereas Brian correctly points out there'll be less existing use conflict. A seaweed farm's permit in federal waters is the same application you would send to the Army Corps of Engineers for all intents and purposes for an outhouse. We do need regulation that's going to enable farmers to get in the water in federal waters, and then in state waters, we need to have that societal dialogue. Is this something we want? If we want it, where should it be done and how should it be done and to what extent? And that's really the hard part. So to scale that, we're going to have to change hearts and minds.
Thanks, Paul. So a couple of the questions. Thanks, folks, for putting them in the Q&A. We've only got about 5 minutes left, so anyone can jump in on this one if you like. But I get asked this sometimes: how do these sorts of solutions compare cost-wise to other solutions that are out there? What's the business case for why would we spend money on these that might cost more to remove per ton of carbon removed or avoided versus other solutions that are readily deployable? So Brian, I see you got your hand up, and then Paul.
Sure. No, I think that's really key. You know, if we get to zero carbon, but it's on a dead planet, will we really have succeeded? I think we have to find an integrated solution that's going to address food security for billions of people during times of climate disruption. And we're talking heat waves and droughts. We're talking about major failures in other regions that could be flooded. And the nice thing about the kelp harvest of 35 million tons, as Paul so aptly described, is that it doesn't require any land area and it doesn't require any fresh water. So if we can regenerate life in the oceans, and we're talking enough food for humanity at the same time that we have enough food for nature, and we can regenerate those decimated offshore ecosystems, whether it's thousands of square kilometers of kelp forest or millions of tons of fish that have actually been pulled out of the oceans and hasn't been regenerated. This produces the habitat and in fact the feed that's needed for those fish to regenerate. Get those ecosystems back on track and restore natural upwelling, get the oceans going again, give nature half a chance, and she will rebound with exponential bounty. It's estimated that there's 100 gigatons of carbon dioxide fixed in the ocean each year. And about 10 of it is exported out of the surface ocean, the middle and deep ocean. So we've got a chance at multi-gigaton scale to help nature get back on track and fix carbon while she's feeding the world and ensuring healthy ecosystems. So this is all about getting back to a healthy climate. And, in many ways, the oceans is the climate. It's 99% of the livable biomass, environment. And it's also, a huge fraction of the thermal inertia of the planet. So if we can get the oceans back on track, we'll go a long way to getting back to a healthy climate.
Thanks, Brian. Paul, and then I'm going to give Leslie the final word.
Excellent. So this is one of those activities, seaweed farming on the ocean, that is really triple bottom line. You're going to create. Give me a patch of ocean and some kids with good strong backs, and I can create food. I can create an ocean with better water chemistry, and I can create profit. So it's not so much about cost. It's about, can you create profit with it? And if you can, then that's going to drive scale. And seaweed farms have been profitable for centuries. It's a question of sizing the farm, the approach, the species, and the market for the particular area you're farming. But it's been demonstrated it can be done. We just need to scale it.
Great, excellent. Thanks, Paul. And Leslie, final word, final thoughts to you.
Yeah, when we talk about economics, it costs something to restore Arctic ice, but we're talking, depending how large an area we're thinking about, perhaps a few $1 billion per year. That sounds like a lot, but when you're preventing or reducing the risks of these larger methane releases that really are one of the loaded guns pointed at our heads as far as climate goes, and the risk of the mass extinctions that will accelerate if we do that, and the billions of people displaced with no livelihood, no place to live. It's a pretty small cost. That's $600 billion just in the last few years that have been lost to climate devastation in one country, the US, is a pretty good example of it takes a little bit, okay, calling $1 billion a little bit, but it takes a much smaller amount in order to reduce the risks of having an uninhabitable planet. So it's very important. It's sort of the due diligence of let's keep our planet able to support life and us.
Well said. Well said. Thank you. Thank you, all three of you. What I love about these are like practical solutions that are happening right now, and that could be deployed. So it's, we all know the climate crisis and the impacts, and it's time for, let's get some solutions in the water and on the ice, and let's tackle it. So I love it. All right, Sumitra, I'll hand the reins back over to you. This has been such a great discussion. Thank you, everyone. Thank you, all of the participants as well. I wish we could have many more hours to dive into all of the details of this, but we'll have to end there. So thanks so much.
Thank you, Jeremy.
Thank you, Jeremy. Thank you to our all panelists. Very grateful for such an inspiring conversation. Thank you for joining. Now we'll move on to our networking portion of the day. And that is the last section of our event. For networking session, please feel free to stay off camera. Use the chat box to send direct messages to attendees. In your messages, you may include your name, contact information, and preferred timing. Connect now or after the conference. So with so many people, we are not going to have a live in session today. Please connect, mute your camera. We'll share contact information after the conference as well. And you can save your messages and the chat box by Save Chat. Thank you all for joining the webinar and enjoy the networking session. Thank you.